Well, folks, back a little bit quicker than I had expected to be, but yeah, I'm enjoying this. So let's just keep at it for another one. I'm going to do one more video here for this evening, and then I definitely will park it. And in this video here, what we'll do before we go into meshing is we'll manipulate a few of the parameters in the design point table to get it working in a little more streamlined way of a flow. But what I should have also did before I finished off the last video and before we finished up in Design Modeler all the time was create our named selections, which I'll just do that now. Okay, so you could do this in meshing as well, but I prefer now just to do them in Design Modeler because I like seeing the named selections there in the meshing workflow because it gives me the option that I could select a region to be meshed by either geometry or name selection. So selecting these first two outside regions, I'll just right click onto them and then I'll go for name selection. In here, I'll call this the inlet. Okay, out at the back here, right click onto that, name selection, where are you? Oh, I need to generate the last one, apologies. Oof. And then let's go now for name selection. This is outlet, generate. Now the bottom one, all of these here, in the different face zones, right? 3 of them, right click that, name selection. I'm going to call this one wall hyphen track. Because it's effectively a solid surface. It's a track. I'm going to select the tire. Oh, I need to generate wall track. Okay, select the tire. Name selection. Let's call this one wall hyphen. You got it. Tire. And then what we'll do as well is inside here, I'm going to select the airfoil itself. Right, and then generate that first. Select the airfoil. Right click, name selection. Let's call this one wall hyphen ME, main element, because there'll be other walls for the different elements as they come. Main element. Okay. And generate. The other thing I was thinking about doing is just when I was contemplating coming back in and doing this video, and I said, oh, maybe I will do it because I should have put in the name selections. I also thought about the wheel and the tire. Now, I didn't put that in as a parameter, change the position of the hub of that wheel tire. So as this track comes up and down, I suppose it is connected onto that, should come up and down and with it. But what if I want to give it more squish or that? I'm going to put this in as a parameter because the other thing is in Fluent, if I'm going to specify that boundary as a rotating boundary, I need to put in a center, I need to put in an axis of rotation. If that changes at all here, I need to update that in Fluent, so it'll be as handy for me to have that out in a parameter table. So what I will do is that is in the, I can't mind which airfoil profiles, sketching, airfoil profiles, it's not in that one, flow domain, yeah, here it is here, yeah, V5 is there, sketching, modeling, sketching, where are we at, V5, values 205, far field, there it is there, V5, 205, let's make that a parameter, and actually see what I call it, let me see, call this wheel hub height, that'll make some sense, and the rest of the flow domain ones. Okay, that's really I think all I wanted to change in Design Modeler itself. All right, so I'm going to X on out of this. Let's pause that while this is happening. Okay, that's closed up. So we're back out here onto the parameters table. One of the last things we were looking at, projects parameters. Geometry's done, we're down into meshing. But I want to do a little bit with these parameters here just before we move on to meshing. But what I'll do here first is I'll save this Save as, let's go into documents, answers, and let's go for formula student, I'll go 26 wing underscore front dash 2D. All right. So this is my table of design points. I'm not so worried about this just now at the minute. Most of my work is going to happen in here in the outline schematic for the parameters and the properties table down here. So effectively all I want to have to do is change my scale and change my angle of attack, and I'll want, for instance, this wheel, well, that'll not really change. That's set off to 700 millimeters. I should be able to change that. But what I should be able to do is change that based off of the tire diameter. So let's just do that. Let's just start with that one. What if I put in a larger tire? Then this here is obviously going to be affected, because this here is also a function of the radius, right? So this is 700 millimeters plus the radius. So the radius is based on this 414.02 diameter at the minute, which is 207.01, which is this added on to the 700. So let's change this expression, right? So the expression is actually going to be equal to 700, right? Let's specify that with millimeters in a square bracket. Let me take off the caps locks. 700 millimeters plus, right? The tire diameter divided by 2. So the tire dia divided by 2. Tired, oh yeah, stupid. It definitely is getting late. You don't put in the parameter name, you put in parameter ID P3. Apologies. There it is. So that's at 907. But you'll see now, if we go over to the table of design points, it's grayed out kind of. It's a darker shade. It means there that we're not changing that. That's being driven by another parameter. In this case, it's going to be tire diameter that's driving that. Right. So I change my tire diameter. It'll automatically update the position of my the X position of my wheel accordingly to make sure that there's a 700 gap maintained. Now the hub height I'm going to keep the same at 205. This is the big one here, right? This is the leading edge to track height, which is laid out here. This leading edge to track height. Right? Every time I change the angle of attack, I need to change this, which means in Workbench here in the parameter table, or up here in my table of design points, if I change that to minus 10 degrees, right, I could change that to minus 10. But look, wheel to LE to track, leading edge to track is stayed at 85.29, but that's incorrect. Right? 85.29 is for 15. At 10 degrees, this should go to 97.28. Right? But it hasn't. Let's do that back to minus 15. Right? It hasn't. So what I want to do is I want to write in some function here that will update the this distance as a function of the angle of attack, and indeed of the scale, and indeed of the height above the ground. Right? Because this one here, the LE to track takes into this value, takes into account this value and this value, as you could see it here. Right? We have our Y11 value, this value, right, multiplied by our Z8, which is 550 divided by 100, gives me the 5.5 scaling factor of the 100 mil chord. So it's a function of that. I need to divide that there by 10 and multiply it then by this, and then I need to add on 42 plus Z9. So I want to try to reflect that. I want to try to do that automatically, but what that means is I need to get a relationship between the two of these. Now, what I'm going to do is I'm going to do a chord fitting exercise for this, a little bit of regression line on it, and I'm going to leverage MATLAB for that. But first, let me just add in a new parameter here and call this ride height, because this is going to be a driving parameter. What I'm going to do, I'm going to put this into small letters. Don't know why I put the other ones in. Ride underscore height. All right. give me 1 second, I have a little bit of a think, but yeah, I'm going to also put in a new parameter just when I'm here, and I'm going to write it. I'm going to put this as height trailing edge main element. I can write in a function for that. But at the minute, the ride height, I'm going to set this in by 42. Now, notice there it doesn't give it a parameter. So if you write it, create a new parameter outside in this parameter table here, it gives it as a dimensionless unit. Now, if I can go into my expression here, and I can open up a square bracket and put in millimeters, close the square bracket. Oh, it says there it has to be dimensionless. All right, apologies for that. 42 for writing it out there. So it'll be the same with the height of the trailing edge of this. But let's write in an expression for the height of the trailing edge. So I know that the height of the trailing edge is going to be the sine component of the chord length for that given angle. Right? So what I'm gonna write it out here. The height sine. So the sine of the angle of the AOA will be equal to H. So O is going to be equal to the sine of AOA multiplied by my chord length. Okay, so if I was to write an expression for that, I can start off with sine of AOA dot ME. Now, AOE dot ME is being shown up as a degree here, but I would be very cautious about writing it in here that it's not looking at for it as a radian. Right? But we'll just check that. If it is looking at it as a radian, what we're going to have to do is multiply that by 180 divided by pi. But let's go for this at the minute. Sine of AOA dot ME, which I don't want to write that, it's actually P2. P2, sine of P2 multiplied by, we're looking at our scale ME multiplied by 100. So multiplied by 100 multiplied by P1. So the height there is at minus 142.35, which cannot be right. Definitely cannot be. Oh, plus, that'll have to be plus a 42, won't it? Because it will have to be up over the track height. So that would be only the height relative to the leading edge, or the start of the kind of the chord. But what I'm going to do in this one is I'm going to multiply that there by pi, or multiplied by 180 divided by pi. Now I don't know, will it recognize pi as a function? Let's just see. It does. But let's put that into minus 357. Why would that there be? Oh, the angle of attack is minus number on this. Multiplied by minus 1, 357. Which can't be right. So this could be measuring it in degrees. Let me just take out my 180 over pi. 142.35. Sounds about right. And then what I need to do is I need to add on my ride height plus P7. 187. So at the minute, I'd be saying that the trailing edge of that, main element is 184.35 millimeters above the track. Now, why is that important? It's because another regulation in Formula Student states that the front aero element, the maximum height on the front aero element cannot be greater than 250 mil. That's what it is. I'll just double check that, but that's what I'm believing it is. So I know at 15 degrees on a 5.5 or 550 chord length aerofoil, the trailing edge will be 184.35 mil above the ground for a 42 mil ride height. So I'm well within my regulation there. Right. So let's now look after our leading edge to track this, so this updates straight away. So this is what I'm going to do. I'm going to come on into MATLAB. I'm going to go into home. I'm going to import some data. I'm going to take myself into that spreadsheet, file data, which is in the app that's in use. So let me just close that down. Appler coordinate. All right. So a little bit of core fitting. So we're either going to run with possibly a second order polynomial or an exponential function or a power law. I doubt a linear will help us any. And this is the data I want to bring in. My angle of attack to my my leading edge to low point height. So this is going to be a dependent variable. This is the independent variable. Right? So let me just scoot in these two things of data. Let's import away, and that'll write a variable. Let's close. Yeah, don't need that. Right, and what we'll go on ahead is into apps. Let's go to curve fitter. Select the curve, so I'm going to select some data. X data. It's this one. Y data is the variable 25. Close. And that there is using a first order polynomial or straight line fit straight through the data. Having a look at our goodness of fit metrics, R squared 0.9982, we probably can improve on that. Root mean square 0.0446, it's not superb. 13 degrees of freedom, not bad, we're using plenty of them there. But if we go second order, yeah, our R squared is way up, is good. Our degrees of freedom we've come down slightly, which isn't really what we wanted. But you know, our adjusted R square, yeah, we're very good at that. I'm just going to check the exponential function. Curiosity 998, that is very good as well. 13 degrees of freedom is superb there too. Yeah, the exponential function seems to work very well with that. Maybe slightly better than the second order polynomial. Let's check the power law. Unable to fit X, that is non-positive. Right, so I should have normalized that there. Obviously the power law will not be able to fit on that. But however, the exponential function seems to be pretty good. If I was to run with the exponential function, that would be the function here. So my A value would be 16.2774 by the exponential function of B to X, which will be our angle of attack. Now we'll try writing out that. I wonder, does design modeler or workbench take in exp, an exponential function? We'll give it a check. So let me just write down that function. So f of x is equal to a, which is 16.2774 multiplied by the exponential function of b, which is 0.0484 multiplied by my AOA, my angle of attack. All right. So let's close this on down and see what we can, if we can write this in here. So 85.29. So instead of 85.29, let's go for, this has to come out to millimeters as well. 16.2774. So if I just put that in, yeah, that automatically prompted as millimeters. 16.2774 multiplied by exp. Don't notice it use the exponential function, we'll soon find out, of 0.0484 multiplied by AOA ME, which is P2. Now this is going to give an error because the units will not be solid, but I want to see, does it bring up anything about the exponential function. resolves to I. So it does see EXP, but it's just that we need to take off our the current argument resolves to quantity with a radian unit. So what I'm going to do is I'm going to multiply by 1 with a unit of radian raised to the power minus 1, close bracket. Now, it's not a valid, so this is not a valid quantity for length. So what I'm going to do is I'm going to multiply the whole lot of this by 1 millimeter, or 16.0642 at 15 degrees. So let's just see what our height was in the spreadsheet for that. And you open the spreadsheet again. Obviously, it's going to be different because I need to scale this up for a 550 airfoil. Don't forget this was the function just for the 100 millimeter airfoil. So at 15, this is showing me it's 7.87. This is showing me it's 16.0724, which is not correct. So let's see what we need to get. That's in radian. So this is measured in degrees. That's probably why. So what we're looking at P2 multiplied by that. This is actually going to be P2 multiplied by 180 divided by pi. And you put that back into degrees, I believe. 7.87567. 7.87. Yeah, so that's it. So I have all of that. Now what I need to do is I need to multiply this by my scaling factor, multiply by P1. Let's bring me to 43 point that. And now what I need to do is I need to add in my track height, or my ride height, which is 42 multiplied by 1 millimeter. So I need to, this is a separate term, I need to have the same units in it. So for a minus 15 degree angle of attack, my leading edge to track should be at 85.3162, 85.29. It's not bad, not bad. I'm 200ths off. Is it 3.1? Wasn't it 200ths off? Right, let's just test it. So then if I go to, say, minus 10 degrees, this has put L2 to track to 97.1759. 97 at minus 10, 97.28, 97.17. It's not bad. All right, I'm at 1100ths off there. It's not bad, 1100ths of a mil. The polynomial function, we could have maybe tried the polynomial function in this one. It might have came back a little bit better, but you know, when we look at the data fit, you know, some are up, some are below. It just depends on what range we're at. The 10 here, our fit, we're down below. Whereas, you know, if I went to minus 12, I'd be slightly higher. So we're not bad. It's not a bad fit. You're not going to pick up all of these. And it's also bearing in mind that I took these measurements off of AutoCAD, so I wasn't exactly snapping on to the curve at the right point. So then that data itself could be carrying an error as well. So I'm happy enough to go with that sort of a function. That's working out very well. But what that now leaves me is that I can change my angle of attack. It updates my length to track here. Even if I bring this down to, say, 4, to 400 mil airfoil, my track, that's updated as well as the height. Everything's being updated now based off of inputting only really 2 parameters, or 3 parameters. That are going to be my 3 main parameter inputs, which are going to be the scale of the airfoil, the chord length, the angle of attack of that airfoil, and also the ride height, 42 mil. Right? And drop that ride height now up and down. So I have the power to do all that out here in the design table, or design points, right? And change my scale, change my angle of attack. I can then change down here my ride height. You know, ride height would be handy to move it up. Change that. The wheel hub, my 205 is going to be the height of that. I'm probably not going to change that. No, it's probably a waste having it there. But there you are. My tire diameter. Probably not going to change that just for these assessments. But there you are. We'll have that. But there we go. I'm happy enough to do that. There might be some more filtering to do with the parameters after we do the meshing, and certainly whenever we do the solver, the fluent solver will be outputting lift and drag and L over D and pressure coefficient and them bits. So yeah, we'll be able to see how they resolve within this table of design points. And yeah, keep developing, see what sort of results we get out of these and how well this workflow will actually turn out to be. So yeah, I'm going to cut video 2 now short, and I'm going to look forward to getting into video 3, but it certainly will not be tonight. So yeah, thanks again for joining. I hope maybe that you learned something a little bit new, you've seen something that you liked. If you didn't like it, let me know. If you liked it, let me know as well. And I hope to see you in the next video. Thanks very much.